bound to the food matrices, whether it is in hydrate form, whether it is with the capillary, whether it is in the within the solid chemical hydrates. Okay, so there are many types of bound water. Okay, so unbound water, okay, is also there. Okay, and also free water is there. So free water is something that is removable. Now even in the under the free water, it could be some of the bound water and unbound water. So that part we have already talked about, we have looked at it, right? So how does it look like? So let's say, so this is our moisture sorption isotherm. So this is uh, our MSI. Okay, so let's say up to this. So this is EMC, or equilibrium moisture content, and here we have water activity, right? So let's say up to this is okay. So this is, let's say, total moisture. Total moisture. Okay. Now up to water activity 1. So at water activity 1, what is the moisture we call it? Anyone? Anyone? Up to water activity 1. So any water content or moisture content at water activity 1 and less than that, what is that? Last
Bound.
class,
Bound
bound
water.
water.
Unbound
Bound.
moisture content.
No, this is bound water, right? So this is the unbound moisture, right? Right? Now,
Yes.
what is free moisture content? See, if you have 30% RH, I am taking this example. So water activity of the food, let's say it will be 0.3. Let's say 0.2, 0.3, something like that. It is graduations are there. So when it is in the food is in equilibrium, when food is in equilibrium with drying air, so having 70 degrees C temperature and 30% RH, food will have water activity equals to 0.3, right? Is it okay? Right?
Yes, sir.
So this corresponding moisture content is basically the equilibrium moisture content of the food. Okay, so this is the EMC in food. So this part is the free moisture content. So this is the free moisture. Fine. So this free moisture, this can be removed during the drying process. And you can see this free moisture can be the sum of unbound water and bound water also. Right? So you understand that means while drying process is going on, this unbound water and bound water is there, and it influences the movement of water from the food to the surface. All right. So what happens? So initially, let's say it has a thin layer of the moisture. Okay. So at first it gets evaporated. Now what happens? The water within the food, it moves to the surface. Okay. And due to capillary action. All right. And that part of water also gets evaporated, okay, during drying process. Okay. Then what? Then what happens? This water layer, okay, or water level within the food, it goes down. Okay. So air goes in, it is sucked up within the capillary. Okay. Then what happens? The movement of water basically by, we call it diffusion process. So I will go into the detail. And all this process and what I told you, I will, go into the detail in a moment. This influence the, total drying rate. So you can imagine, suppose you think of, suppose you have a, water in a bucket, okay, or water in a, in a glass. So if you try to, evaporate this water using this hot air, so it will be much more easier, right? This is free water, so nothing is there. Now suppose this water is within the food, okay, so the same amount of water you will have the difficulty of removing it because how the water is present in the food. Okay, clear to you?
Yes, sir.
Okay, so now what we will do, so so now the thing is, what we do in the, when you go for the experiment to determine the, rate of process when we conduct experiment. So initially we know what is the moisture content. So let's say moisture, okay, and time. Okay. Initially we know the moisture content at 0 time. Okay, let's say here is the W1, W2, W3, and W4, and dot W E. Why we are saying E is the equilibrium moisture content, because up to that we can remove the moisture. We cannot go, below that level, because this one is the equilibrium with the hot air. Okay. So time is, let's say, T1, T2, T3, T4, and TE. Okay. So these are the weight we are taking. Okay. Now what we do, we plot them. Okay, so after plotting, so this is total moisture. So after plotting, the how we get usually the traditional how it looks like. Okay, so here let's say we have total moisture. Total moisture. Total moisture. Let's say this is in dry basis, kgH2O per kg dry solid. Okay, this is in x-axis. We have time in hour. Okay, so the way it looks like, I will explain what are those points. So here is, so if we plot it, so we will get this kind of curve. Okay, now when we talk about the, total moisture in kg H2O per kg dry solid, we express, let's say, in terms of a different um, uh, you know uh, uh, nomenclature. Let's say total moisture is xt, x total, capital X total. Okay, that is equals to W, okay, minus WS divided by WS kg H2O per kg dry solids. Oh, so this is in dry basis. So WS is the weight of solid. Okay. Rather I would say this one, not moisture. Okay. This is the weight of food. That is what actually we monitor. Okay. So all right. So W is the weight of okay, food. That means weight of moisture plus dry solid, weight of dry solid. Okay, let's say in kg, in kg. All right. So W minus WS, what does it give us? Total amount of moisture. Okay, so total amount of moisture present in food kg. So this is the total amount of moisture divided by amount of solid. Okay. Now how we get this in a dry solid? We expose the food material to 105 degrees C for 4 to 6 hours. Okay. So we can get the, we call it sometimes bone dried solid also. Okay. Now let's say, so well here. Now this is the total moisture we are plotting. Now so the typical curve look like this. So A, B, there are some points, D and E, A, B, C, D and E. Now what are those? So that's the thing. Okay, so I will at first explain few terms, then I will come in a moment. What are those points and what does this signify? Okay, so that means up to this point we can say we have XT total moisture, right? Fine. So this is the one is XE. What is XE now? So XE we are saying is the equilibrium before I write this one, I will just write one thing. So let's say X is the free moisture. Okay. X is the free moisture. Okay, so don't confuse it this one with the X total. Okay. Free moisture KgH2O per kg dry solid, which is equals to Xt minus Xe. Now what is Xe? Xe is the equilibrium moisture content, so in dry basis. So this is also in dry basis. So KgH2O per kg dry is KgH2O per kg dry. Okay, that means this is equals to We minus Ws divided by Ws. All right. Is it okay to you?
Yes, sir.
Okay. Now this, what is A, B, C, D, E? Now let's write this one. So AB, this part is the warm up period. It will be more clear to you. I will draw another curve, okay, another graph that represent the rate of drying with the moisture content. Okay. So AB is the warm up period. BC is the constant rate drying period. Okay. Now CE is called falling rate and period. Okay. So C is total is the C2E is the falling rate drying period. Now CD is the fast falling rate drying period. Okay. Fast falling rate drying period. DE is the second falling rate drying period. Can you just give me a minute? Sorry for the interruption. Okay. Now I will come one by one. Okay. Now the thing is, here you say we are saying constant rate drying period, falling rate, and under C it's a sum of CD and D, first falling rate and second falling rate. So here the rate is coming into the picture. Now why it is called constant rate? Why it is called the falling rate? Okay, so that part is very important to understand. Now I will just briefly tell you for now. So constant rate is where then a rate of drying is remain constant throughout this period. Okay, so rate of drying remain constant. Okay, in the falling rate, the rate of drying keeps on changing. Okay, so that is the main significance. Now, if I plot this rate factor with the moisture content, how do they look like? Okay, so let's do it. So let's say this is here in x-axis we have total moisture content. Total moisture content. Okay, we are saying. Now here is the rate. Okay, so rate of drying on the y-axis. Let's say this is R. Okay. Now total moisture content. So where to start? Whether it will start from this side or this side. So you remember initially the moisture content is high and it is gradually going down. That means it will start from somewhere here and it will go to this side. Right? Okay. So I will draw it. So this is A, B, A prime, C, D. This is E. Now, can you tell me why this has not touched the this origin 0, 0? See here.
All
Yes.
the moisture will not be removed.
Right, because here we are considering total moisture content. Right. If I would have written the free moisture content, then it could have been right here. Right. because after drying the free moisture content will be 0. But you cannot remove the total moisture. It will go up to the equilibrium moisture content. So this is up to, so this one will give you, so this is actually XE. This is corresponding to XD. This is, let's say, XC. Okay. And this is A and B. Okay. Now, so this is A, B or A prime B. Now the thing is, so what we said, it's a, AB is the warm up period. Now what happens? So let's say the AB or A prime B is called warm up, sorry, period. Okay. Now why here we have A and A prime? So what happens? So suppose your food has initial temperature of let's say 50 degrees C. Okay. Initial temperature of 50 degrees C. I'm saying, okay. Now your drying air, it can have temperature, you can use either 60 degrees C or you can use 40 degrees C also, hot air. It depends on the the type of food we are using. So if you have a very heat sensitive food product, then usually go for the lower temperature. If you have a not that much of heat sensitive, so we go for the 60 degrees C. Now what happens? Let's say you have 50 degrees C. So for when this is exposed to hot air, so what it will do? It will try to equilibrate this one with the temperature of the hot air. So it will either go to, if it is 40, it will be 40 degrees C, or it will be 60 degrees C. Now when the suppose it is exposed to 60 degrees C, that means the temperature of this one will rise. So during the rise, the evaporation will be faster. That means rate of drying will be faster. So that follow AB. That means from initially it was at less temperature, so it quickly reaches to there sudden increase in the rate of evaporation. Okay. Now if this is 40 degrees C, okay. Now what it will try to do? It will try to equilibrate itself with this air of the 40 degrees C. So since this is the lower temperature, the rate of evaporation will go down for the initial some few minutes. So that will follow from A prime to B. Is it clear to you?
Yes, sir.
Okay. All right. Now B to C is the constant rate, right? So that means you can see that throughout the whatever. So here it is XB. Okay. So from here to here, from XB to XC, the rate of drying doesn't change. It is parallel to the x-axis, and this value remain constant. Okay. Now the moment it reaches to C, okay, so C to E is the falling rate. So you can see this is CD, this is the straight line, and DE is the concave upwards. Okay, so this is first falling rate, this is second falling rate. Okay, so not necessarily it has to be there. It could be either straight line also throughout this period, or it could be like that. I will just draw it. Okay. Either it could be just a straight line. Okay, I'll draw it later. Okay, just I want to explain it. Or it may follow, for initially is the straight line, then concave upwards. Now what is XC? So XC is called critical moisture content. Why it is called critical moisture content? Because after that the rate of drying changes with the decrease in the moisture content. C to D is the first falling rate and D is the second falling rate. So C to D is the first falling rate. Straight line. D to E, second falling rate. Concave upwards. Now there are significance. Why does it follows straight line, why it is follow the concave upwards. Okay, that part now I will be covering. Okay, all right. So let's start with the description with the constant rate, then this one and this one. Now, as I said, it could be this also. Okay, so here you have a R, you have X. Okay, A prime, B, C. Okay, so then it will be E. There is no in between. D is not there. Okay, it could be like that also, complete straight line. Okay, or it could be like, sorry, so here like this also. Like this also. Okay, so the many possibilities are there. Just I am giving you some example. Okay, so it depends on the type of food we are using. All right. Usually for the vegetables, I would say, yeah, I think for the vegetables or grains. Okay. For the vegetables, usually follow this nature. Okay. For grains, follow this one. Okay, cereal grains. Okay. Anyway, so just I will start from now. Constant rate period. Okay, so what does actually constant rate period says? Okay, so B2C is the constant rate drying period. Okay, all right. So drying. Rather, I would write it over here. Description of drying region. Okay. All right. In this period, rate of moisture removal from the product is limited by the rate of evaporation of water, okay, from the surface and within the product. Okay, so the moisture in food act as a free moisture. Okay, as a free moisture. Okay, that is not bound to I would rather say in a different way. Act as a free moisture that is not bound to the food. Act as a free moisture free moisture that is not bound to the food matrices. Okay. The drying rate remain constant as long as the migration of moisture from the food body to surfaces at which the drying rate remains constant as long as the migration of moisture from the food body to surfaces okay, I would rather write in different way. As long as the migration of from the is enough, as long as the migration of moisture from the food body to the surface is enough for evaporation taking at the surface. Okay. Okay. So surface is initially wet. I would say rather very wet. Okay. Very wet and continuous film of water exists in food surface. Okay. So in this case, the water is entirely the unbound water. All right. So during this period, you will have the constant rate drying period. Okay. Now, we will have the, so this part is clear. That means that water act as a free water. That means let's say water in a bucket. Okay, it's a completely unbound water. So the water, I would just say, the water is entirely the unbound water. Okay. All right. Now coming to the falling rate period. So this is BC. So C2 C2 C2E is the falling rate period. Okay. After reaching the free critical moisture content, that means XC, okay, free critical moisture content at point C. Okay, the drying process proceeds at decreasing rate. Okay. All right. Now what happens? All right. So here you see, if you look at this one, this is the sum CD and DE. There are two. Okay. So we will now focus on this part, initial part, CD. What happens in the CD? Okay. So in the fast falling rate period, sorry, that means C to D. Okay. The saturated surface area. That means, as I said, here I have written that the surface is initially, that means you can consider it as a saturated. Okay. The saturated surface area decreases as the moisture movement within the solid. Okay, within the solid. Okay, within the solid can no longer supply moisture. Okay, so as the drying rate decreases, unsaturated surface area increases. Okay, now when the entire surface area become dry or unsaturated internal moisture movement controls the drying process. Okay, that means, so see, initially, say this is the food. Initially the surface was the continuous film of water exists during the constant drying period. Okay, now as soon as it reaches to the critical moisture content, so this part actually becomes, so the surface actually become exposed to the hot air. So that means it is no longer a saturated surface. There is no continuous film of water exist. Okay, in some part there is a film, but it is again getting dried. So you can see, if you look from the top, is a patch of some water, patch of some water, patch of some water, patch of some water. So these are the water. So the other areas are, the shaded areas are actually unsaturated surface area. Okay. Now, when I say this internal moisture movement controls the drying process. Now, how the internal moisture movement takes place? Okay, so in the first falling rate, so if you look at the structure of the food material, so if I draw it, so if you have food, there are lot of capillaries present. So I mentioned that capillaries are present, right? Macro capillaries and micro capillaries. So in micro capillaries, water is more bound. In the macro capillaries, the water are unbound. Okay, so macro capillaries, as long as they can supply the water, it's fine. Okay, but in the micro capillaries, they are actually not able to supply the water at that rate. So the capillary water, so capillaries are there, and they are actually internally connected. Okay, now water, so when this water is getting evaporated from the surface, so water from inside goes to the surface, okay, through these capillaries. Okay, through these capillaries, water go to the surface. Now, when these waters also, recedes, okay, because of the drying, so there will be some small layer of the water in level of the water within the capillary. So what will happen to the voids? So air will be sucked in. Okay, so when the air will be sucked in, okay, so there will be no continuous film of water within the food material, not in the surface, not within the food particles. Okay, so that comes under the this part DE. So during this period you will have, this is actually called, we call diffusion control drying. CD is the, this is because of the this capillary movement of the water, that is called the capillary movement within the food product. So that is actually, we call it a funicular drying, another one is the pendular drying. Okay, so that I will just write it. What is the time? Okay, I still have 10 minutes. Okay, so capillary movement, in solid. Okay, so this is under actually first falling rate, you remember. So this is under first falling rate, that linear part of the straight line part. Okay, so solids or foods, you can say, are porous material, and they have interconnecting channels and pores. Okay, so as water evaporated, okay, a meniscus of liquid um, liquid means water. Okay, meniscus of water is formed around each pores and channels. Okay, so it gives the capillary force, actually capillary force, okay, by interfacial tension. That is very important. By interfacial tension between water and solid. Okay, so the capillary force provide water movement, provide driving force for water movement. Driving force for water. Okay, so you understand. So by the capillary force, water is coming up. Okay, so when it starts receding, this layer also, so air will be sucked in. Okay, so air rushes to fill the gap, actually, void in the channels. Okay, so that is called, actually we call this process of funicular drying. So this is actually basically driven by the capillary movement. Okay, so so water is brought to the surface, okay, by capillary force, when the water recedes below the surface level, air sucked in to fill up voids and fill up void. This process is called funicular drying. Just give me a minute. Hello. Okay, so I think today is up to this. Okay, so did you understand?
Yes, sir.
Okay, so this is actually, this is the first falling rate. So first falling rate, so this straight line. So this is actually capillary controlled. Capillary controlled drying. Second part, I will talk about it later in the next class. So this D2E is called the diffusion control drying. So that means when it reaches to D, so as I am saying, so here is the, the air sucked in, okay, so it goes down, it is no longer provided by the capillary movement, the water. Now what happens? So during that time, so the temperature of the food material, it increases quite high. Because initially when the water is quite high in the initial period, it also provides some cooling effect. Okay, now water amount is very low during this drying process, and you are supplying, let's say, 70 to 60 degrees centigrade water. So when it reaches to that level, 60 to 70 degrees hot air, so at this level what happens? So there is no continuous film of water around the food particle exist. So during this time there is no capillary movement. The water is brought, or it is being evaporated by the diffusion. And how the diffusion occurs? So the waters, within the food matrices, water gets evaporated and condense, evaporate and condense. Okay, so that is why it is called pendular drying. So that's how it moves within the food matrices, and eventually water gets out. And so that about that I will discuss more in the next class. All right. Okay, so today up to this. Okay, so I think maximum I will need 2 more classes to finish. Yeah, so today is 21st, 24th, and yeah, by 28th we will be finishing. Then I will give you assignment. Okay, so because your exam will be starting from 7th, I will give a week. On 4th we can discuss if you are having any problem. Okay, and then you are good to go. All right.
Yes, sir.
Okay. So any question? Okay. So if you do not have any questions, you can leave. No problem.
Thank you, sir.
Yeah.
Okay, sir.